Hi, it's Nova again, and I want to welcome you to Module 4. Today we're going to explore one of the most important inventions in astronomy, the telescope. In this module, you will learn all about the telescope and its current incarnation as a digital computer. Let's start this module with some basic facts about the telescope. First, the telescope was invented in Holland in 1608 by Hans Lippershey, a spectacles maker. Next, there are two basic types of telescopes. The first one is a refracting telescope, which uses a combination of glass lenses to bend light rays to a focus. The second type of telescope is the reflecting telescope, which uses mirrors to bring light rays to a focus. Third, in 1610, Galileo was the first astronomer to make a telescope and apply it to observing the night sky. And last, the reflecting, or mirror telescope, was invented in 1668 by Sir Isaac Newton. In a refracting telescope, the primary lens bends, or refracts the light, as it passes through the glass and brings it to a focus to a small inverted image. In a reflecting telescope, the primary mirror, which is a concave piece of glass with a reflective surface, forms an image by reflecting the light. This is a photograph of Newton's original 1668 tabletop reflector. Now let's take a look at the light ray path in Newton's original reflector design.
So Newton is bouncing the light rays off of the mirror in the back of the telescope and having it come out the side as an eyepiece for easier viewing.
A refracting telescope uses a primary lens to focus starlight into an image that is magnified by a lens called an eyepiece. The primary lens has a long focal length, and the eyepiece has a short focal length. A reflecting telescope uses a primary mirror to focus the light by reflection. A small secondary mirror reflects the starlight back down through the hole in the middle of the primary mirror to the eyepiece. Storing and analyzing light from space is key to understanding the cosmos, so the invention of photography in 1839 was really the start of modern astronomy. It has been a little over 170 years since we've been able to store and analyze the light from space. This is the world's first successful celestial photograph. It is an image of the sun made by French physicists Fizeau and Foucault in April of 1845. With the advancements of photography, traditional film storage of light from space has now been replaced by a computerized light storage device. This device is called the Charge-Coupled Device, or CCD camera. When light from a telescope is focused on a CCD, an electric charge builds up in each pixel in direct proportion to the intensity of the light falling on that pixel. When the exposure is finished, the charge on each pixel is read into a computer. A charge-coupled device is a specialized computer chip containing roughly 1 million microscopic light detectors. These are arranged in an array and are about the size of a postage stamp. In this image, 40 CCDs combine to provide up to 378 million light-sensitive pixels that store images on a computer. All digital image capture devices are technically known as charge-coupled devices.
This includes all your phones. Every phone is a charged coupled device recorder.
Here are two views of the same part of the sky. On the left is a negative photographic plate image. On the right, you can see a CCD negative image. These images were made with the same telescope. Not only can CCD chips replace photographic plates, but they have some dramatic advantages. They can detect both bright and faint objects in a single exposure, and are much more sensitive than photographic plates. They can also be read directly into computer memory for later analysis. Telescopes are placed in outer space primarily to avoid the distortion of light caused when it passes through the Earth's atmosphere. So we've learned a little about the telescope. Now let's explore the nature of light. Light is a form of electromagnetic radiation. Therefore, it is a form of energy. Historically, white light, or sunlight, was considered pure and perfect. But the truth is that white light consists of all the colors, so it isn't pure or perfect. It was believed that the colors in the rainbow, or in a glass prism, were false due to scattering in the atmosphere or the glass. In 1670, Newton proved that colors were primary. Today we say that a beam of white light is separated into its component wavelengths, each of which appears to the eye as a different color when dispersed through a prism. So white light is actually a mixture of electromagnetic waves of different frequencies, each of which produce the visual sensation of a particular color. The term spectrum, which we use to refer to the rainbow of visible light, was coined by Newton. So color is the Roy G. Biv part of a much larger electromagnetic spectrum. Roy G. Biv is a common acronym that is used to remember the colors of the rainbow or a glass prism. It stands for red, orange, yellow, green, blue, indigo, and violet. These images show that colors were a primary nature of sunlight. In 1666, Newton bored a small hole in the window shutter of his bedroom to admit a thin beam of sunlight. When he placed a prism in the beam, it spread the light into a beautiful spectrum that splashed across his bedroom wall. From this, Newton concluded that white light was made of a mixture of all the colors.
In the bottom image, Newton had another idea. Maybe the 7 colors were made up of more colors, so he put a second prism in the dark room with him and let each of the colors pass through. And as you see here, yellow stayed yellow, red stayed red, and so forth, and that was his proof that the colors were primary. There were no other colors.
This figure shows the range, or spectrum, of electromagnetic waves. The human eye can only detect light waves in a very short frequency band of the EM spectrum. Infrared radiation has lower frequencies than those in visible light, and ultraviolet radiation has higher frequencies. Then, there are the still higher frequencies of X-rays and of gamma radiation from atomic nuclei. Last, please note that the spectrum of visible radiation is not the source of heat from our sun. Infrared is invisible radiant energy that has longer wavelengths than those of visible light. William Herschel discovered invisible infrared, or heat rays, in 1800. Using a series of thermometers, Herschel recorded temperature changes caused by the bending of the invisible rays of the sun through the prism. William Herschel drew this graph in 1800 depicting the maximum intensity of solar radiation or heat. Note the gray graph of heat shows that the maximum energy appears beyond the visible color region discovered by Newton. If light is not pure and perfect, but is instead made up of 7 colors, none of which are the source of heat from the sun, then what are the colors? We learned earlier that Newton said the colors are primary. What does that mean? Well, neither Newton nor Herschel could quite make a definition for what light is. It was not until after the discovery of electricity, the electric charge, and the nature of magnetism in the early 1800s that the understanding of the nature of light would emerge. By the early 20th century, science was so conflicted with itself over this problem that Albert Einstein and Max Planck created an entirely new theory of radiation, the quantum theory, in an attempt to understand the behavior of radiation at the atomic level. After Exam 1, the behavior of radiation will be our first topic of discussion in Unit 2. This blue marble image of the Earth was taken using the Visible Infrared Imager Radiometer Suite, or VIRS instrument, aboard NASA's most recently launched Earth-observing satellite, SWAMI MPP. This composite image uses a number of swaths of the Earth's surface taken on January 4, 2012. The MPP satellite was renamed SWAMI MPP on January 24, 2012, to honor the late Verner E. Swamy of the University of Wisconsin. SWAMI MPP is NASA's next Earth-observing research satellite. It is the first of a new generation of satellites that will observe the many facets of our changing Earth. SWAMI MPP is carrying 5 instruments on board. The biggest and most important instrument is the Visible Infrared Imager Radiometer Suite, or VIRS.
We looked at telescope infrared. Okay.